The primary way to test and revise a scientific theory is by using what's called the hypothetico-deductive method. So this involves 5 steps that go in a circle. So in other words, after you finish step 5, then you go back to step 1. So step 1 is first construct or choose a theory to explain or interpret a phenomenon, some observations you've made. And then step 2 is to derive a hypothesis from that theory about a phenomenon that you should observe if the theory is correct. Step 3 is to test this hypothesis by conducting an empirical study. Step 4 is to evaluate your theory in light of the results of your hypothesis test. And then, like I said, step 5 returns you back to the start. So now that you have this new information, you need to either revise the theory or construct a new one if necessary, and so on. So it goes in a circle. That's how science is. The scientific method is never over. We're always getting more and more advanced. So you can think of it as a circle, or more accurately, you should think of it as a spiral. So yeah, it's going around in a circle, but it's also advancing to something. It's going somewhere. So yeah, that's the primary way to test and revise hypotheses. But here's an example of the hypothetico-deductive method in action. So, based on the research literature, a researcher constructed what we call drive theory. This refers to how being watched by others while performing a task will cause you to become physiologically aroused. You know, your blood's going to start pumping. You're going to start breathing more heavily. You might start sweating. And this will increase an organism's tendency to make a dominant response. So by dominant response, I just mean if you're very good at doing something, you'll get better. If you're bad at doing something, you'll do worse. That's the basic idea. So this drive theory explains how physiological arousal due to being watched by others can lead to social facilitation for well-learned tasks and social inhibition for poorly learned tasks. So, based on this theory, the researcher hypothesized that he would observe that the presence of others will improve performance in a simple task, but inhibit performance in a difficult version of the same task. And to test this hypothesis, he had cockroaches run down either a straight path, which he considered to be the easy task, or a cross-shaped maze, which he considered to be the hard task. And the way he did this is perhaps exactly how you just imagined. Think of this tiny little, hallway with clear walls and cockroaches on the other side of the wall. He took one of them, put them in the hallway, and then observed how that one would act when surrounded by its peers. So that was the experimental condition. And then there was also a control condition where the cockroaches would run down the hall by themselves. What he found was that the cockroaches in the straight runway would reach their goal sooner when they were in the presence of other cockroaches, while those in the cross-shaped maze took longer in the presence of other cockroaches. So that seems to support the original theory by confirming this hypothesis that has lent some support to drive theory. So that's how this relationship works. You create a theory, you derive a hypothesis, you test that hypothesis, and then based on the results of your test, you either revise or construct a new theory. That's all there is to the hypothetico-deductive method. But obviously, each step in this process can, be a bit complicated. Like when it comes to constructing a new theory, this is one of the more challenging parts of research. It requires a lot of creativity. the most important aspect of constructing a new theory is just basically doing your homework. You have to understand what other researchers have done. You have to have read the previous literature to really be able to, come up with something new. It's quite likely if you haven't done your homework, you're going to have some brilliant idea as to how something works that some other guy thought of 100 years ago. So you just need to make sure that your new theory is truly new. And the only way you can do that is by reading what's been done in the past. And compared to what's been done in the past, your new theory should be more formal. So it should be more precise, provide a more accurate explanation. It should be broader in scope. It should be able to explain a wider range of phenomenon. It should be more parsimonious, so it should include less unnecessary parts. And it should just provide a new perspective or approach. You want to contribute something new to the discussion, something that other people haven't already thought of before. Also, if you find yourself a pioneer in some particular field of research and nobody has ever really talked about this kind of phenomenon before, then pretty much anything you come up with was going to be useful. So yeah, I mean, when I say useful, I mean it's going to help advance the discussion, but you still want to try to come up with something that is parsimonious and relatively broad in scope and so on. So when it comes to doing this, when it comes to trying to meet these requirements, you need to consider the ingredients for your theory. I call them ingredients, but what I'm referring to are just the previous research. So all theories come from previous research. Everybody's always just standing on the shoulders of giants, to put it metaphorically. So whenever you evaluate some new theory that's been proposed, the best way to see how good it is just to look at what it's based on. Look at, what the researcher used to make it. So if you want to just get a quick evaluation of any new theory that's developed, the best place to look would be the references list. But if all this sounds a bit too complicated, doing all this research, doing all this creative thought and trying to, refine something that nobody's ever really even thought of before, if that sounds beyond your scope or your timeline, then you might just want to go with an already established theory. It's much more common, in fact, for researchers to start with an established theory than it is to construct a new one, because of how time-consuming it can be. But whenever you do this, you need to make sure you give credit where it's due. To avoid any kind of plagiarism, you need to make sure you include citations to that original theory in your research paper. And when I say that this is easier, I don't mean that it's like the lazy way to do it. In fact, in many ways, this is the better way to do it, because science is all about collaboration. It's all about standing on the shoulders of giants, so to speak. We help each other, we comment on each other, we share our notes. So whenever you take somebody else's theory into a new direction, you're helping each other and you're just advancing our general scientific understanding. So this is by far the preferred method. And one of the things I was mentioning early in this video is that the whole point of doing this kind of stuff, coming up with new theories or trying to take a theory in a new direction, is to then be able to make predictions based on it. Hypotheses always come out of theories. So a theory would be the general explanation, where a hypothesis is a specific prediction about particular phenomenon being observed under particular conditions. And whenever it comes to theories and hypotheses, you should always think of it as like a if-then kind of relationship. For example, if drive theory is correct, then cockroaches should run faster through an easy maze when observed by others than a more difficult maze if being observed by others. Now, there are multiple ways to derive hypotheses from theories, including asking a research question and then determining if there's an established theory out there, which implies an answer, or first identifying and focusing on a particular theory and trying to take it into a new direction, something that has not yet been directly observed. In other words, you could start with the hypothesis and then look for a theory, or start with the theory and then look for a new hypothesis. You could go either way. And generally, the best hypotheses that you can develop help to distinguish between competing theories. There are a lot of scientific debates out there, and testing new hypotheses can help to settle those kinds of debates. And if your hypothesis is confirmed, if we do provide a lot of evidence to support your hypothesis in systematic empirical research, then that will just add strength to the theory it comes from. Like, not only did this theory make an accurate prediction, but now there are new phenomena that that theory can account for. On the other hand, if your hypothesis is not confirmed, if you don't get any evidence to support it, then that will make the theory seem a little weak, perhaps. It'll make the theory seem a little bit shady. And if researchers continuously come up with new hypotheses that fail from a particular theory, then that will really start to make the other scientists look at that theory in a bit more of a critical light. Perhaps that original theory wasn't as good as we first thought. So, along with many other methods that I've previously discussed, hypothesis testing is actually a really great quality control for our scientific theories that we have out there. There have been numerous examples of theories that have been pretty well established, only later to be taken down because we just continuously fail to support them. But that's just another example of something I talk about a lot. You know, there is no truth in science. Science has never actually proven anything. Scientists typically try to avoid even using that word prove because it implies that we have the final answer. That's not how it is, obviously. Theories that we have, theories like gravity, theories like relativity, these theories can only be strengthened or weakened. They can never completely be eliminated or completely be proven. It's just impossible. And here's why. Let's say we have the most accurate theory we've ever developed. You know, we've never observed any examples that it could be wrong. Well, that doesn't mean that we couldn't prove it wrong in the future. You know, there might be other plausible theories that could be better. Even if the one we have is excellent, there is always room for improvement. There's always a better way to explain this phenomenon that we're interested in. And it's always possible for a new hypothesis that comes from that theory to either lend additional support or to do the opposite and make that theory start to seem a bit questionable. And if we, as I said, if we continuously do that, if we continuously come up with new hypotheses and they keep weakening that theory over time, this will lead to what, you know, most people would call a disproving of the theory. Typically, that just means we've abandoned it. You know, some researchers might still want to do research on it, but the vast majority of the scientific community has moved on to alternate theories that haven't gotten so much criticism over the years. But the reason for that is, the reason why we never fully abandon it is because there's a lot of reasons why a hypothesis could fail. A hypothesis test could fail. Like maybe the researchers used a poor design. You know, maybe the hypothesis is actually very accurate, but the researchers just don't know what they're doing. Like they use the wrong methods, they use the wrong participants, or something weird just happened. Whatever the reason is, there's a lot of potential explanations for why hypotheses fail, and that's why we are never fully satisfied with either accepting or rejecting a theory.